Hi, my name is Ben Owens. In this video, we're going to continue our discussion on hypothesis testing. A hypothesis test is used to determine whether a value, usually an average or proportion, is significantly different from some other value. Often, this original value is coming from previous knowledge or experience, and the hypothesis test is used to determine whether there has been a significant increase or decrease from that original value. In the last video, we discussed that there were three different types of tests: a right-tailed test, a left-tailed test, and a two-tailed test. The type of test depends on what you're trying to prove. If you're trying to prove that a quantity is bigger than or has increased, you're going to use a right-tailed test. If you're trying to prove that a quantity is smaller than or has decreased, you're going to use a left-tailed test. And if you're trying to prove that a quantity is different, but you don't specify whether it's bigger or smaller, then you use a two-tailed test. Also, when you're doing a hypothesis test, you can choose your level of significance. As you can see, as the alpha level gets smaller, the area to the outside gets smaller, which means that it's a stronger test. So you can test the significance depending on the severity of the outcomes. And that way you can, if there's a very severe outcome, you might want to have a very small alpha value. But if it doesn't really matter, you can have a larger alpha value. There were three different formulas that we are going to use for test statistics when we're doing hypothesis testing. And they're all basically the same, but we use them in slightly different scenarios. The first formula here is when we use this when we have a sample that is large and that we're trying to find the sample average. The next formula is used when we have a sample that is small, say less than 100, or the original standard deviation is not known. That is, we have to rely on our sample standard deviation. The final formula we use when we're performing hypothesis tests involving proportions. In this video, we're going to be looking at a couple of examples. Example 1. A study from 2007 found that in a certain city, 89% of the residents had cable TV. Now, with the rise of Netflix and Hulu and other online television providers, a researcher thinks that this percentage has decreased. A sample of 450 residents finds that only 384 of them have cable. Can the researchers conclude that the percentage of people with the cable has gone down at the alpha is equal to 0.01 level of significance? So the first thing we need to do in solving or using a hypothesis test is we need to state our null and alternative hypothesis. In this case, what we're trying to prove is that the percentage has actually gone down. And so the alternative hypothesis is that p is less than 0.89. That is less than what it used to be. Of course, the null hypothesis is going to be that p is the same or is equal to 0.89. When dealing with hypothesis tests, what you're trying to prove is always the alternative hypothesis. In this case, it's a left-tailed test because we're trying to prove that the percentage has gone down. And looking at the alpha is equal to 0.01 level of significance, we find that our critical value is negative 2.33. Basically, this means that in our test statistic, if we get a number that's less than negative 2.33, then we'll reject the null hypothesis and accept the alternative. However, if we don't, if we get a number that's greater than negative 2.33, then our results are inconclusive. So here, since we're dealing with proportions, we're going to use this formula for our test statistic. Now, calculating p hat is just finding the sample proportion, which in this case would be 384 over 450, which is 0.8533. And so plugging those into the appropriate places, we would find that our test statistic is negative 2.49. Now we compare this number, our test statistic, with our critical value. Since the test statistic is less than the critical value, we say that it's in the rejection region, therefore we may reject the null hypothesis and accept the alternative. What that means is, based on our evidence, we have strong reason to believe that the average or the percentage has gone down. That is, that it is less than 89% now. Let's look at this example. A pollster is interested in whether the average number of hours of TV watched weekly in a certain city is different than the national average of 35 hours per week. A poll of 23 people is taken, and the sample average is found to be 33 hours with a standard deviation of 6. Can the pollster say that the average is different at the alpha is equal to 0.1 level of significance? Now notice, in this case, we're trying to find whether the average has changed, and our sample is rather small. Because of that, we're going to use the t-distribution. So our null and alternative hypothesis is going to be that the average is not equal to 35. Notice that in this case, the pollster is not trying to determine whether it's increased or decreased, but only that it's different. And so our our alternative hypothesis is going to be that the average is not equal to 35. And of course, our null hypothesis is that the average is equal to 35. So here we have a two-tailed test. Now, using this information, since it's a two-tailed test and the alpha level is 0.1, we need to divide that into 2. That is, we need to consider alpha divided by 2, which is 0.05. Since we have a small sample, we're going to look at the t-distribution with 22 degrees of freedom. And if we look at the column for 0.05, we find that t is going to be plus or minus 1.717. That is, if we get a number that's bigger than 1.717, then we reject the null hypothesis, or less than negative 1.717, we reject the null hypothesis. With a two-tailed test, the critical region is actually on both sides. So our test statistic formula is here, and therefore plugging in the appropriate amounts, that is, what we observed, the sample average, minus the national average, divided by the sample standard deviation over the square root of n, gives us the value of negative 1.599. Since the test statistic is not in the rejection region, that is, it's not less than negative 1.71, we fail to reject the null hypothesis. Therefore, we do not have enough statistical evidence to conclude that the average is any different. So one interesting question is this. Are hypothesis tests always correct? That is, if we choose to reject the null hypothesis, does that mean that it's true that the average or the proportion has changed? Well, since the test statistic is calculated from a sample that is randomly selected from the population, it's possible for a hypothesis test to simply be incorrect. There are two ways that a hypothesis test can get it wrong. We call those type 1 errors and type 2 errors. Thinking back to example 1, the one that was dealing with the cable TVs and the percentages, what if the actual proportion in the city was still 89%? That is, if this were the case, our sample proportion said that it was 85.33. What if that was just an unlucky sample, but the actual average was actually still 89? Then, since we rejected the null, we would have kind of gotten it wrong. Now, since the alpha level is 0.01, we expect that this is going to happen about 1% of the time. What happened was, we rejected the null hypothesis when it was actually true. This is called a type 1 error. When you reject the null hypothesis when it's actually true, that's a type 1 error. A type 2 error could occur when we had, like, the situation in example 2. Thinking back to that example, dealing with the average number of hours people watched on TV, we failed to reject the null hypothesis. Now, if we failed to reject the null hypothesis when it was actually false, that is also an error, and we call this a type 2 error. These errors, or actually all the results of a hypothesis test, can be summarized in this formula. Along the top here is what we have in reality. In other words, this is what's actually true. On the left-hand side here is what we got from our test. That is what our decision was, either to reject or fail to reject based on our sample. Now, if the null hypothesis is true, and we fail to reject the null hypothesis, meaning that we don't have enough evidence to say that it's not true, then our hypothesis test is correct. On the other hand, if the null hypothesis is false and we reject the null hypothesis, that's also correct. It's when we have these other two scenarios that we have what's called a type 1 and type 2 error. So if the null hypothesis is true and we reject that hypothesis, that's what we call a type 1 error. If the null hypothesis is false and we fail to reject, that's called a type 2 error. Often, the variables that are associated with the probabilities that these types of errors occur are alpha and beta. I like to think of this analogy dealing with what could happen in a trial. So suppose that someone is on trial for a crime. Now, in reality, that person can either be innocent or they can be guilty. And the results of the trial, they can either be found innocent or they can be found guilty. Now, if the person is actually innocent and they're found innocent, then this was a correct judgment. In other words, you got it right. And if the person was actually guilty and they're found guilty, this is also a correct judgment. That is, the hypothesis test is correct. However, if the person is actually innocent but they're found guilty, then we have a type 1 error. And the probability that that occurs we call alpha. On the other hand, if the person is actually guilty and we find them innocent, that's what we call a type 2 error. And the probability associated with that is beta. Now there's an interesting relationship between alpha and beta. They're actually what we call an inverse relationship, meaning as one value goes up, the other value goes down. A good way to think about this is using our justice system. In our justice system, we like to make sure that an innocent person will never go to jail. That is, what we're trying to do, to the best of our ability, is to make sure that if you're actually innocent, that you're not convicted or you're not tried as guilty. Statistically, what we would say is that in our justice system, we try to minimize the value of alpha. That is, we want the probability of this happening to be as small as possible. Of course, what happens is, if we try to make the alpha value as small as possible, then we're going to sort of open the door for the beta. That is, we're going to probably allow more actually guilty people free. That is, we're going to find them innocent. It's kind of a give and take. Now, if you were in another society that did not want anyone who was guilty to ever be found innocent, that is, if you were trying to minimize the beta value, then you would probably end up maximizing or making the alpha value very big. In other words, you'd probably find a lot of innocent people guilty. This is the interesting give and take between the type 1 and 2 errors. Another way of illustrating this is to think about where these people would land and where we have our standard of judgment. In other words, the standard of judgment here can be thought of as how strictly the court system is. Now, in this case, this represents all the innocent suspects, and if these innocent suspects are on the right-hand side of the line, that's going to be people that were found guilty although they were innocent. That is, that would be those type 1 errors. On the other hand, here are the criminals. It says the smart criminals with top-notch lawyers. The ones of them that fall on the left-hand side of this, that is, that get a not guilty verdict, well, they also got it wrong, and that's going to be a type 2 error. Now, if you can imagine, if you were to slide this standard of judgment to the right and left, if you were to move this line to the right, it's going to decrease the number of innocent people that you find guilty, but it's going to increase the number of guilty people that you find not guilty. Of course, if you slid the bar this way, then you're going to minimize the number of people that you say are not guilty, but that's going to make bigger the amount of innocent people that are found guilty. As you can see, here we have this relationship between alpha and beta. I hope you found this video helpful in understanding hypothesis testing and type 1 and 2 errors. Thanks for watching.